Hello everyone, this is Professor Keen. We've been talking about beam breaking. This is from a Student's Guide Volume 2, Chapter 6, which is from Galileos Dialogues, the second day. You might remember in the last lecture we were talking about how you can figure out how hard it is to break a beam that is projecting from a wall. So I've reproduced part of this diagram here where I show a beam that is sticking out of a wall. So here's our wall. Right? And you might think of this as being cemented into the wall. This is a beam that's sticking out. And we might imagine applying a transverse force to the wall. So imagine applying a downward force right here, a transverse force to the wall. And if we think about this as producing a moment, so the distance from the fulcrum, this is this distance right here from the fulcrum to the point you're applying the force, that is the lever arm, which is just the length L. So we can say that the braking moment is equal to the transverse force times the lever arm. And then we can think of the beam having an internal resistance, R, that is trying to hold it together, and the lever arm that it is working with goes from the fulcrum up to the point of application of this resistive force. And so the supporting moment is equal to R times d over 2. And what's going to happen as this transverse force is increased larger and larger, this resistance meets it. Basically, it increases so as to meet it, but it can only get to some maximum resistance. And because the diameter doesn't change, that means that there's going to be some maximum supporting moment that the resistive force can apply. And so if the braking moment ever exceeds the supporting moment, then the beam breaks. And it will rotate, it will then fall down in this direction, it will rotate down that way. So that will be the braking that happens, okay? All right, so that's where we were last time. Now, let's go on to some of Galileo's propositions. Okay, so let's look at proposition 1. Proposition 1, and this is, if I remember correctly, this is about page 76. I don't have the text right in front of me. Proposition 1. And what he says here, these are not the exact words he uses, but I'll put it into my own words. So he says the longer the beam that is sticking out of the wall, the easier it is to break. The easier it is to break with a transverse force, like we've been considering. Okay, that might sound intuitively correct to you, right? I think, keep in mind that you've been alive for however many years now, and you've been watching the world for all those years. And so the fact is you do have some intuitions about the way things work. And you can probably imagine that if you have some stick sticking out of a wall, the longer it is, the easier it's going to be to break it. Now what Galileo is trying to do is provide some tighter geometrical reasoning for why this is the case. Well, let's go back to this idea right here. When the braking moment exceeds the supporting moment, then it breaks. So if the braking moment is bigger than the supporting moment, then it breaks. Well, what is the braking moment? We already calculated that. It's just the transverse force you're applying times the length. And so what is the supporting moment? Let's make that an S. It's the resistive force times d over 2, right? Let's rearrange this formula a bit. Let's move the L to the other side so that when the transverse force is greater than R times the diameter divided by 2L. So I've rearranged that a little bit, then it breaks, okay? So if the transverse force is greater than whatever the maximum resistance that it can exert times the diameter divided by 2L. Now, here's the thing to notice about this formula. Notice the following. that the transverse force required to break it, probably see where I'm going with this, is proportional to 1 over length. Proportional to 1 over the length. Notice the length is in the denominator. So the longer it gets, the bigger the denominator, the smaller the transverse force required to break it. So the longer the beam, the smaller force required to break it. Smaller force required to snap it. Which is exactly what our intuition would have suggested. But now we have a way of mathematically modeling exactly how much easier it should be to break. So for example, if you had a beam of a certain length and it took a certain force to snap it, if you doubled the length, then it should be half as easy to snap it. If you triple the length, it should be a third as easy to snap it. It should take 1/3 the force. If you have the length, it should be twice as hard to snap it. So there you go. We have a way of thinking about it. Also notice that the transverse force required is proportional to the diameter. So the thicker it is, the harder it is going to be to break it. Okay, so it tells you kind of how these dimensions of the rod affect the force required to break it. And that is what Galileo is bringing out in his first proposition. We have time. Let's go look at the second proposition. Proposition 2, and this is on page 78 in the text. What is he doing here? Well, he's saying, let's suppose we have some board, a wooden board sticking out of a wall, and the question we ask is, how does the orientation of the board affect the ease with which it breaks? The orientation of a board, let's move this over to here, projecting from a wall, from a vertical wall, just like the other one, affect the ease with which it breaks. With which it breaks. So I'll draw some pictures. So you might imagine, first of all, having a board sticking out in this orientation. I'm intentionally making it kind of a thin board. Okay, so imagine that's the board, and here's the wall from which it is sticking out. And let's suppose this is orientation 1. It's kind of like a diving board sticking out of the wall. And let me put some dimensions on here. So the thickness of the board in this direction, we'll call that D1. Let's call the length of the board from there to there, we'll call that length of board 1. And let's suppose we then apply a transverse force down here. We'll call this force 1. That's a transverse force. Of course, I didn't draw the back end of the board. This is the part that's sticking into the wall. And, back here you have the resistive force with which it's being supported by the part of the board that is inside of the wall. So maybe I should draw a little bit back here. There's some board sticking into the wall, and that resistive force is what's holding the part that's sticking out of the wall to the part that's sticking in the wall. Okay, so that's case 1, or orientation 1. Now what about orientation 2? If you took the exact same board, but instead of orienting it horizontally, let's suppose you were to orient it vertically, like this. It's supposed to be the same board. I hope I make it look about the same. Okay, and this is the part then again that's in the wall. Okay, same board. So now the dimension, I guess the thickness right here, whoops. Thickness here, again we have thickness right here. Whoops, I guess I want to get rid of that because I don't even want to emphasize that. That doesn't matter. Now we have D2, that thickness right there, which would have been the width of it over here, but now it's the height of it, okay? And here we have length 2, which is exactly the same as length 1, so these are the same, okay? And now we apply a force, a transverse force right here. And the question is, which one do you think is going to break more easily? Is the force 1 required to break this beam going to be bigger or less than the force 2 required to break this beam? And I suspect that you probably already know the answer to this, that it's going to be much easier to break this beam than this beam, even though it's the exact same beam, they're just oriented in different ways. So why? Why is it that it's easier to break this beam than to break this beam? Well, let's see if we can figure out why it's easier. So remember here, we came up with a formula for the transverse force required to break a beam. It goes as the longitudinal resistance, R, times the diameter, the thickness, divided by the length. Okay, so that's going to be, if the force exceeds that, then the beam breaks. So let's compare force 1, I'll write it up here, the force required to break beam 1, to force 2, the force required to break beam 2. So this is this right here, this, all right here, required to break beam 2, and this one is the force required to break beam 1. Of course, it's the same beam, they're just in orientation 1 and orientation 2. So let's find the formula F1. It's just resistance in case 1 times the diameter in case 1 divided by twice the length in case 1. And force 2 is resistance in case 2 times the diameter in case 2 divided by twice the length in case 2. Okay, I know this is getting a little bit messy. Let's go down here where I have a little more room. Force 1 is to force 2, like this. Well, R1 and R2, I forgot to draw R2 in here. That's the longitudinal resistance. That is the strength of this beam to be coherent to the part inside of the wall. Well, it's the exact same beam, so R1 and R2 are going to be the same. So these two are going to just cancel each other out. Okay. Notice also that you've got a 2 in the denominator of both cases. Those are going to cancel each other out. R1 and R2 cancel each other, 2 and 2. What about L1 and L2? Those are the same. They stick out of the wall the same distance. Oops. So those two are going to cancel each other out. So let's cancel those. But notice that D1, the thickness here, and D2, the thickness there, are different. Okay, so let's write that as D1 over D2. Everything else canceled out. Okay, so notice that because D2 is much larger than D1, D2 is bigger, force 2 is going to be much larger than force 1. That is, it's going to be much harder to break beam 2 than beam 1. Why is that? Well, you can kind of see it here because this resistance is acting with a larger lever arm because of the height of the beam than this resistance. Over here, that resistance, it doesn't provide a very big supporting torque because it's got a small lever arm between the line where the fulcrum is. So this is the fulcrum line, I guess. And that resistance only takes advantage of D1 over 2 as the lever arm, whereas this one, the fulcrum line, once again is right here about which it's trying to rotate. This is the lever arm. It's got a much longer lever arm, so this resistance, I guess, is more efficient at holding it up, right? So it's going to take a bigger force to break it when D2, because D2 is bigger than D1. Okay, so that gives us away once again the law of the lever, and using the law of the lever provides a way of understanding some things that are probably intuitively clear to you, but maybe you haven't thought about this in the kind of geometrical way that that Galileo is using here. Okay, we'll stop